Okay, so this is chapter 4, dealing with force diagrams, free body diagrams, friction, normal force, weight, all that stuff. Okay, so what I'm going to do is consider the different cases. Oh, excuse me. So I'm going to consider the different cases that could come up for questions in this chapter. The first one being a non-accelerating object on a level surface. Then an accelerating object on a level surface. Let's see. Just every case that we've talked about. Then there's also these two cases for a sloped surface. The cases where there is an object being pulled straight up or down by a tension force, or maybe just hanging in equilibrium by a tension force. So all these different cases, and for each case I'm gonna work like an actual problem that might be given. I can't work every single combination for everything that might be given, but just for each case I'll work an actual problem that could be given based off of whatever the situation is. Okay, so first case, let's start with I said a non-accelerating object on a level surface, but really let's start with a non-moving object, like a stationary object on a level surface. So this is I guess I could say, the simplest case for some object, for some force diagram. If it's not moving, I'll call this M for mass. If it's not moving, then the only two forces involved are the force, which we could call weight, which is mg, so this weight W is equal to mg. Probably, actually, I think we should use little w for weight, because uppercase W is going to be used for work in the next chapter. Okay, and then we also have the normal force. How do we say? F sub capital N for normal force. In the case of a level surface, on a level surface, no ramps or slopes, on a level surface, the normal force is directly opposite to weight, this force, mg. They're opposite directions. And in this case, where there's no forces, there's no extra force like pushing up on the thing or no extra force pushing down, then these two forces would be equal in magnitude but opposite in direction. So we could have this relationship that F sub n is equal to mg. Just for force, an object on a level surface. Okay, so where is this coming from though? So, it's pretty easy, I think, to see this relationship, probably pretty comfortable with this by now, and just seeing from the picture and understanding that it's on a level surface that we have this relationship with the normal force in the force of gravity. But recall that this is coming from noting that the sum of the forces in the y direction is equal to 0, since the object is not accelerating in the y direction. A non-zero force would mean that it would have to be accelerating up or down. But it's not it's not even moving in the y direction, so it's definitely not accelerating in the y direction. So the total sum of the forces in the y direction should be equal to 0. We define up to be positive, so when I write my total forces, like as a mathematical expression, the normal force is positive because it's pointing up, and the gravity force, the weight of the object, the force due to gravity, is negative because it's pointing down, and the sum of this should be 0. And that's directly where this natural relationship that I already wrote up there is coming from. Now notice here, I'm not even pointing out the sum of the forces in the x direction, right? I'm not even pointing that out. But I could say that the sum of the forces in the x direction is 0, but maybe that's not relevant to this problem because there's no force pushing back. There's no applied force going this way, and there's no mention of any other kind of horizontal force. Okay, so now recall that any object that's not moving is experiencing static friction, unless the problem has stated to ignore friction. So this object is experiencing static friction right now. So a possible question that I could ask about this is, let's see. Has mass, let's make it not too complicated, 5 kilograms. And let's say it's made of steel, while the surface is made of, now let me see what else we have to work with, and that I'm just citing the list that he uses in the slides here. So steel, let's say aluminum. The surface is made of aluminum. So what's the question? If the object has mass 5 kilograms and is made of steel while the surface is made of aluminum, what static friction force is the object experiencing? So nothing is pushing on the object, but I want to be able to say, like, just as it's sitting there, what kind of static friction is holding it in place? What sort of static friction is holding it in place? So what knowledge do I have to pull? What knowledge do I need to know to be able to solve this? Well, I need to know that my force due to friction that is static, so friction, force that is static friction, is equal to the normal force times whatever the coefficient of static friction is, which depends on the materials involved. So mu sub s, for whatever that coefficient of static friction is, that we'll have to look up, times the normal force. So the coefficient of static friction that I need to look up in the table is equal to 0, wait, let me make sure I'm looking at the right one. Aluminum on steel is 0.61. So I know that just by looking at the table. And now I need to find my normal force, but my normal force in this case is equal to mg, which is equal to 5 kilograms times 9.8 meters per second squared, which is going to be 5 times 9.8, 49 kilograms times meter per second squared, in other words, newtons. So this n here is not the same as that n, right? This F sub n, this n is referring to this force being a normal force, while this n is just a unit of measurement being newtons. So anyways, the force due to friction is going to be equal to that coefficient of static friction times my normal force, which I found over here. So I'm getting 29 29.89 newtons. The unit is still newtons because this coefficient does not have units, so it doesn't change the units in the end. It's still a force, still measured in newtons. So 29.89 newtons. This is just what the object is experiencing just by sitting here, just by sitting on the table. It's experiencing static friction. If I wanted to ask you about kinetic friction, well, then I would have to say something about some other force trying to push this or moving it or something, but I can talk about static friction without an object moving because any non-moving object experiences static friction. So this question, I feel like, is possibly a legitimate question. Another alternative way this could be asked is you could be given this force and asked to solve for some coefficient. Like, let's say they said, maybe the friction force is 50 newtons, find the coefficient of static friction. And then you could manipulate this equation a little bit to solve for that coefficient of static friction. Okay. Alright, so now let's talk about a similar situation, except now the object is going to be not accelerating, but moving. So the previous example, it was not accelerating, but not moving altogether. So now let's, how do this? An object moves with constant velocity to the right due to an applied force. Applied force. So we have, let's see, what question am I going to ask? If the mass is 5 kilograms, so it's the same mass, if the mass is 5 kilograms and it is made, so same materials of steel, and this time it's sliding, it's actually moving on a surface made of aluminum. Let me say, what is the magnitude of the applied force? Okay, so I didn't explicitly state it here, but it's still on a level surface. It's like the same object on a level surface. And this time we're giving it an applied force to the right. So I've got my mass here and I've got some applied force. Capital A for applied force. And I still have my normal force, F sub capital N for normal, the weight, mg, and what else is happening here? What else is happening here? It's implied that there is friction, especially when I bring up the type of material involved. It's implied, heavily implied here, that there is friction. In fact, there has to be friction. Why do I know that? Because if this thing is moving with constant velocity, but there's a force being applied, that means there has to be another force keeping it from accelerating that way. So there must be a friction force, and in fact, since this thing is moving, I'm going to say F sub friction kinetic, F sub k. So F sub k there being friction, which is kinetic friction, because it's moving. So overall, this thing is moving to the right with zero acceleration, though. So overall, okay, So what we should be thinking here is that if it's moving to the right with zero acceleration, well, what can I say? I can start with looking at the sum of the forces in the x direction. So the sum of the forces in the x direction, I know if overall the object's moving in the x direction, but with zero acceleration, constant velocity, right? Zero acceleration, aka constant velocity, then the sum of my total forces in the x direction must be zero. What are the forces in the x direction? Applied force, which if we call that direction positive, then my applied force is positive. My friction force, which is in the opposite direction. And the sum of these, or the total of these two combined, should be zero. Should be zero. In other words, my applied force is going to be directly equal to my kinetic friction force. So this tells me how to find my applied force. I need to find, if I can find this, then I'm done. Okay, how do I find friction force though? Friction depends, excuse me, friction depends on the normal force and the coefficient of, whatever the material is, the coefficient of kinetic friction, right? So let me figure out, well, actually, what would I do from here? I would say, oh, well, my kinetic friction force is equal to the coefficient of kinetic friction times my normal force. There we go. Now I see. And this is by definition, right? We have to know friction force depends on normal force and that coefficient. So now I know explicitly what I need to go look for is the normal force. So now I need to go to the y direction. So I look at my sum of the forces in the y direction. But just like the last problem, this thing is not accelerating in the y direction. It's not even moving in the y direction. So it's definitely not accelerating in the y direction. So the sum of the forces in the y direction is zero. There's only two things going on in the y direction. My normal force pointing up, so positive. My weight pushing down, the gravity force pushing down, which is negative. Their combination should be zero. That means that my normal force should be equal to mg. Put that in there, and I have my applied force is going to be equal to the coefficient of kinetic friction between aluminum and steel times my normal force, which is m times g. And I have to go look up that coefficient of kinetic friction between, it's not the same as the 0.61 we used a second ago because this is kinetic friction. So it's 0.47 times mass, which is 5, times gravity, which is 9.8. So I'm getting 0.47 times 5 times 9.8 is 23.03 newtons. That's my applied force. My applied force must be equal to my friction force in order for something to be being pushed at zero acceleration. Friction must be perfectly balancing with the applied force if the object is not accelerating. So, I can't really fit all this on one page, but there was the question. If the mass is blah, 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 blah. So again, this coefficient of kinetic friction is coming from what I said here, steel on aluminum. Or aluminum on steel, yeah. I don't think it matters if the object is steel and the surface is aluminum or vice versa. It shouldn't matter. And I found the magnitude of the applied force. The magnitude is the size of the force. I could just as easily ask for the direction. The direction is easy though, it's just the direction is to the right, right? If the object is moving to the right, then that force is moving to the right. All right. So let's look at a, oh, did I unpause? Yes, okay. A object accelerating on a level surface. Okay, let's see, what else can I say? The object is made of steel and has mass 5 kilograms. It is sliding on a surface made of aluminum. It is sliding on a surface made of aluminum. That's fine. The force applied to the right that's giving it its constant acceleration is, I don't know, 25 newtons. Find the acceleration of the object. I was writing the question in orange. Oh, well, I forgot. Okay, so find the acceleration of the object. So this is another similar step. We're just making like the next step from something sitting still, something moving with constant velocity, and now something with acceleration. Now something moving with acceleration. All right, so we start with a picture. It's really going to look pretty similar to the last picture with a normal force, with a gravitational force, with an applied force, and a friction force, specifically a kinetic friction force. But overall, the object is moving to the right with some acceleration. How do I know it's to the right? Well, the force is applied to the right. So it's moving to the right with acceleration A. I'll call it A. Not 0, right? Some non-zero number. So, consider the forces in the x direction, which I'll do over here for some more room. Sum of the forces in the x direction last time was equal to 0 because the object was moving horizontally with 0 acceleration, but this time it's not. So the total forces, if overall the object's acceleration, when you account for applied force and friction force, which are the horizontal forces here, overall the object is moving with, due to this acceleration, so overall the force in the x direction is the object's mass times that acceleration, whatever it might be, which is what we're asked to look for. Okay, that's okay, so there's A. Now what about this left-hand side? What are the sum of the forces in the horizontal direction? Well, I've got my positive applied force. I've got my negative friction force. And that's it. That's going to be equal, not to 0 like last time, but equal to some actual force, some overall force due to that overall acceleration. Alright, so the only other thing I can do here is I can go ahead and say my applied force is 25 newtons, but maybe I won't do that yet, but just know that like this, that's going to be easy. I've already got applied force. It was straight up given in the problem. That is what we need to go find. But I do know, I don't want to plug in numbers yet, so I'll just keep writing FA as applied force. I do know that my friction force is equal to the coefficient of kinetic friction times the normal force. By definition, for any problem, that's what it should be. And moreover, in this problem, my normal force will still be equal to that weight, to that mg. Why do I say that? Because the sum of the forces in the y direction is still 0, because the object's not moving up or down, and it's not on a slope or anything like that that would be giving it any kind of vertical acceleration. so no vertical overall force. That means that my positive normal force minus my force due to gravity is equal to 0. In other words, that same relationship we see a lot, where normal force is equal to that mg is happening. So I can go ahead and say that my applied force minus mu sub k, my normal force is equal to mg, and then equals ma. There we go. Plugging in mg for normal force. And now I suppose I can go ahead and solve for a. I'm going to flip this equation around so ma, just to have that ma on the left side, minus mu sub k mg. Can go ahead and solve for a without plugging anything in yet, just by dividing the entire thing by m. And now I'm ready to plug in all my numbers. Fa was straight up given as 25 newtons. Kinetic friction, well, it's the same surface, so whatever it was last time, 0.47 times mass of 5 times 9.8 for gravity, all divided by mass of 5. So I'm getting an acceleration of minus 25 divided by 5, 0.3944 meters per second squared. Okay. So for an object with an overall acceleration on a level surface, this is one way we can find the acceleration. Or, well, this is pretty much the main way you would find the acceleration. There are other iterations of this problem. You could be asked to solve for the coefficient. You could be given the acceleration and maybe asked to find that coefficient, or maybe asked to find the mass. Lots of things you could be asked to find. But with this situation, with an object moving with with an actual acceleration on a level surface, this is going to be kind of the defining relationship. The overall acceleration times the object's mass should be equal to whatever the applied force is minus that friction force, with the friction force being dependent on the normal force, but in this case the normal force is just mg. This is going to be kind of the defining relationship for any problem that deals with an object on a level surface sliding with a constant acceleration. Well, a non-zero acceleration. All the problems we're dealing with here are if there is an acceleration, it's definitely constant. At least for now. Yeah, that's going to be the big one there. The defining equation for a situation like this. All right, so now let's look at things moving vertically. So let's look at, okay, so let's look at vertical motion now. So we've considered strictly horizontal motion. Let's look at vertical motion now, except the first case there's going to be no vertical motion, but at least vertical forces. So let's say an object is suspended by a rope. So it's not moving up or down or left or right, it's just suspended by a rope. If the object's mass is 19 kilograms, find the tension force in the rope. Okay, so let's draw a picture, some object, some ceiling here, and then some rope holding the 19 kilogram object. Alright, so my forces, I'll use a different color just to show them a little bit better, especially right here. I've got a weight, always, right, gravity, mg, and then I've got a tension force, not a normal force, right, because a normal force is given by a surface pushing on the object, like the table or the desk is pushing up on the marker right now because it's touching a surface, but there's no normal force for an object that's suspended like this. Alright, I want to find the tension force. So I can say, well, look at the sum of the forces in the y direction. I could look at the forces in the x direction, but why, right? There's nothing going on in the x direction. The object is just suspended by a rope. The rope is directly like vertical. There's no weird like angled ropes or anything like that. So I'm just going to look at the force in the y direction. If it's not moving, suspended, it's not being pulled up, it's not being dropped, then the sum of the forces in the y direction is 0, because overall there is 0 acceleration. There's 0 movement, so there's 0 acceleration in the y direction. My two forces, if I define up being positive, then my tension force is positive, my mg is negative, and together they should sum or combine to 0. This gives me this nice relationship, very similar to the normal force relationship, right? With weight. And there we go, just plugging in 19 times 9.8. 19 times 9.8. So that would give me 186.2 newtons, which is a lot of force, but 19 kilograms is, you know, I suppose a fairly heavy mass, like 40 pounds or something like that. So, fair bit of force, fair bit of tension in that rope, a fair bit of tension force in the rope. And that's it for a object suspended by a rope. So now what if we have an object being pulled? So I want to, before I look at an object being pulled up by a rope and looking at the tension force, I want to look at one of the problems in the slides where we're looking at the normal force for an object being pulled up with acceleration. So let's see, how do I word this? All right, I think I've got a question here. And a 10 kilogram object is sitting on a scale in an elevator. The elevator begins to accelerate upward, upward with an acceleration of 2.5 meters per second squared. What mass, no, how do I, let me think about how to say this. Okay, what does the scale read in newtons? So this is like a scale, you know, that gives weight in newtons. What does the scale read in newtons when the elevator is accelerating? So this is not a tension force problem necessarily. This is an elevator that is being pulled up by a tension force, but we're not really worried about it. We're more like zooming in on the thing inside the elevator. So we have the elevator. We have this scale, I guess, and then some some object, some 10 kilogram object here sitting on the scale. And we have the motion that we are concerned with is the upward acceleration. So there is an upward acceleration with A equal to 2.5 meters per second squared. Upward acceleration at 2.5 meters per second squared. What about the forces? What about the forces? Well, inside here we have the normal force of the object, and we have, of course, the weight mg of the object. And we also have this overall force, right, due to this acceleration. So if we were to draw a, or rather if we were to investigate the sum of the forces in the y direction, what would that look like? Well, the sum of the forces in the y direction should be not equal to 0 here, right? There is an overall acceleration of 2.5 meters per second squared, so there is an overall force, a positive force going up. Okay, that's the overall force due to this acceleration. What are the smaller forces that are involved here? I have my normal force pointing up, I have my mg pointing down, and together these should sum to ma. Okay. When I ask what does the scale read, I'm asking for the normal force. Now, why is that the case? Because what's happening here is something that's important to point out is when an object is lifted quickly, if you were in an elevator and it's being lifted very quickly, you feel heavier while it's accelerating upwards. But really what's happening is the surface, the elevator, the bottom of the elevator, is pushing up on you, right? It's pushing up on you, making the normal force greater, right? So when I'm asking what does the scale read, I'm really asking for the normal force. That's an important thing to be able to pull from a word problem like this, is that when in a situation like this, we're asking for the normal force. We're asking for how hard is the, not just from gravity, right? Because in a normal situation, gravity would be equal to the normal force if this was 0 with no acceleration. And if I wanted your, the weight of this object in newtons, you would just say, well, it would just, in that case, that would probably make more intuitive sense that the weight mg is equal to the normal force, which is what we, the past few problems we've done, that's been the case. But when the object is accelerating upwards quickly, like in an elevator, like this, that surface is going to push harder on the object while it's pushing it up. It's like you're squishing the scale between the object and the bottom, and that's going to make the scale read a higher weight. Okay, so I know I'm looking for normal force here. So I'm going to have ma plus mg. And now I'm ready to plug in. My normal force should be 10 kilograms times 2.5 meters per second squared plus 10 kilograms times 9.8, which is going to be 25 plus 98, so 123 newtons. 123 newtons. So the upward acceleration added an extra 25 newtons. This thing would normally read, the scale, let me make a note of that, the scale measured in newtons would normally read, under no acceleration, would normally read how many newtons? Well, mg, right, would normally read 98 newtons, 9.8 times 10. That's just the mg. With 0 acceleration, normal force would be mg. The scale with no acceleration would read 98 newtons. The acceleration added 25 newtons. Whoops, 25 newtons. So how much heavier does it make it feel? Well, you could divide 25 by 9.8 to kind of see how much mass, quote unquote, how much mass that feels like it's adding, if you wanted to, but, well, what would that be? It'd be, is that a good way to describe that, though? Yeah, that's fine. So this is as if the object suddenly weighs, or suddenly has 2.55 extra kilograms of mass. Just by taking that extra 25 newtons and dividing it by 9.8 to get mass, and I get 2.55, etc., etc. So it's as if the object suddenly has an extra like 2.5 kilograms of mass. Okay, so now let's look at an object similar to this kind of situation, an object suspended by a rope, except this time it's going to be being pulled up with an acceleration. Ooh, actually, wait, no, I forgot. I wanted to do a elevator one. Let's build off of this, and say, what if the elevator is going down with a downward acceleration? So let's just build off of this one. I'll say it like this. So the elevator is dropping or accelerating downward, with acceleration, I'll say 1.8 meters per second squared down. What will the scale read? So we expect it to be lighter. We know with no acceleration, the scale should read 98 newtons. With upward acceleration, it read more than 98 newtons. With downward acceleration, the object should feel lighter for a moment, right? With downward acceleration, the object should feel lighter for a moment. The scale, it's as if the scale is being pulled away from the object, making the scale read less. So what will the scale read with a downward acceleration of 1.8 meters per second squared? So the setup is the same. F sub n will equal ma plus mg, but a equals negative, since it's downwards, negative 1.8 meters per second squared. So really my formula will be, when I plug in my numbers, I'm going to have that, oh wait, what was the weight? Oh, not 5, it was 10. 10 kilograms times negative 1.8 plus 10 kilograms times 9.8. Essentially what ends up happening is this part gets subtracted from my original 98 newtons. So I have F sub n equals negative 18 plus 98. So remember, this 98 is what it would read with zero acceleration. And back here, I was adding onto that because I was pushing it up, or the elevator was accelerating up. And now I'm going down, so I expect it to be removed from that value, and I'm getting, what does this, 80 newtons. So it reads less. Okay. So kind of a theme with some of these problems is that these relationships that you get, like this, or like even the one with the horizontal sliding object with overall acceleration, this relationship with the kinetic friction, applied force, and overall force here. There are these relationships that keep popping up, in certain situations. But the thing is that we should never really try to memorize them all, because that's kind of asking for trouble, because there are so many different kinds for different situations. It's better to just understand what's going on as opposed to trying to memorize these different cases. So let's look at now an object being pulled up by a rope. Let me say a 7 kilogram object or mass is pulled upwards by a rope. If the tension force is 120 newtons, what acceleration is being used to pull? What acceleration is the object experiencing? In other words, what is the the acceleration that's being used to pull this 7 kilogram object up with a tension force of 120 newtons? Okay, so we draw a picture. 7 kilogram mass here. Some gravity force, mg. A tension force going up, tension. So, well, I could draw a rope. I've already used the purple to draw the tension force arrow, but there is a rope pulling up, and it's not attached to a ceiling, right? The rope is attached to something that's pulling the object up by with a force of 120 newtons. All right. Looking at the sum of the forces in the y direction, sum of the forces in the y direction is not equal to 0 because it is experiencing an overall acceleration going up, right? Overall acceleration going up. So the overall force will be mass times that acceleration, which is what we're looking for. I have tension force being positive, I have mg being negative, and I have this as equal to ma. See that. Contrast that with this example where the sum was 0 because the object is not being pulled up or lowered. Okay, so now I have, what am I looking for? I'm looking for acceleration, so I can, I'll flip this equation around and put ma on the left side, so t minus mg, and now I'll divide by m on both sides. And now I'm ready to plug in. So A is equal to 120 minus 7 times 9.8, so that's 7 kilograms, all over 7. Let's see, just to save paper, I'm going to say up here. A is equal to, what is A equal to? 120 minus 9.8 times 7, is that divided by 7? 7.34285 blah 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 meters per second squared. Let's round to the 100th place, so 7.34 meters per second squared. There we go. So note that sometimes a problem may give you the object's weight instead of its mass. So note that you could have been given the object's weight instead of mass. So instead of being given 7 kilograms and you had to calculate, what the object's weight was right here with mg, you might have just been told that the object's weight was 68.6 newtons. Sometimes that can happen. It'll say like a object of weight 68.6 newtons, and where does that go? Well, that would just go right here with mg. This is 7 times 9.8. That's what this is. That would be the object's weight. But you would still divide by just its mass here. So if you were given that your acceleration, like when you actually plugged it in, would look like 120 newtons minus 68.6 newtons all over 7. So just keep in mind, if you're given weight, that's fine. Anywhere you see mg in your formula, then this directly replaces that, but you are going to have to find the object's mass. Anywhere, because I had to use mass alone right here in the formula, so I need to know its mass, but it's fine because to find mass, all I have to do is take its weight and divide by 9.8 to get its mass of 7 kilograms. That just might be like an extra small little step you have to do. Ideally, the best thing is if you're just given mass straight up, because that's like the small building block and it's easy to work from. But if you are given weight, you'll probably, depending on the problem, may have to go find mass, just as a little side problem, right? Okay. What's the next one? Okay, so what are we doing now? Objects on slopes. So now moving into objects on slopes and also objects that are held by tension ropes at some angles. So far all the ones we've done no decomposition of vectors. They were all either straight up and down or straight left and right. So there was no cosine theta, sine theta happening anywhere because there were no angles to consider. Everything was just nice up, straight up and down, or straight left or right. So let's consider an object at rest, an object of, I'm going to give weight this time, weight, let's see, I don't want it to be too crazy, 78.4 newtons is at rest on a slope of 30 degrees. Okay, let's say so it's being held in place by static friction, and let's say if the coefficient of static friction is, so instead of telling you the materials and asking you to find the coefficient based off of a table, I'm just going to make up some coefficient of static friction, and we'll just say it's 0.25. Find the friction force, static friction, of course, static friction, things at rest, force holding the object in place. So we got some object on a slope, so some object on a slope of 30 degrees, and it's being held in place by static friction, and we want to know how strong is that static friction, right? How strong is that static friction to be holding an object in place if that's the coefficient of static friction and the slope is 30 degrees. Now, of course, a higher slope, right, the object's going to slide, but we're not really concerned with that here. We're given a fixed slope. Everything is fixed here. We're just asked to find whatever that static friction force is. All right, let's draw it first. So first thing to draw is that slope, and let's see, hang on, before I start drawing it like this. I'm going to draw, I'm looking at the slide, the slides after, what is it? The slide after the table of coefficient of static friction, or coefficients of friction altogether, that slide, I'm not sure what the number is, I can't see. I'm going to orient my ramp the other way, just to keep it consistent with that picture. So my slope is like this. Here's my angle of 30 degrees. Here's some object. And at this time I've told you the weight, right, not the mass. So I don't know the mass, but that's okay. All right, so now I need to start thinking about my force arrows, right? All my force arrows here. All right. Some facts. Normal force should point perpendicular to the surface. The surface always pushes directly on the object, so perpendicular. So that means my normal force is writing right here. Okay. My friction force is always going to be parallel to the surface, trying to keep the object from moving. In this case, static friction is pushing up, right? Because gravity is going to be trying to get this thing to slide down the ramp. So static friction is pushing back this way, trying to get it to not move. So I'll say F sub Fs for static friction. Now, overall, my gravity force is pointing straight down, right here. When I say straight down, I mean relative to the ground. Perpendicular to the actual ground, not perpendicular to the slope, perpendicular to the ground. But the tradition is to, or the way these problems are generally solved, is to consider that when you've got a slope like this, consider that the coordinate axes have been tilted, so that instead of coordinate axes being like x, y, it's like this. Oops, x, y. Right? And why do we do that? Well, because now my normal force and friction force don't need to be decomposed because they are riding right along an axis. Just like all the previous problems we did where the things were riding right along an axis, so there was no decomposition needed, by tilting our axes we've made it so that the normal force and the friction force do not need to be decomposed. Why is that better? Well, because in this case now, only one of our vectors needs to be decomposed, which is gravity. If I were to consider my axes as being tilted normal, so that gravity didn't need to be decomposed, well then I would have to decompose this vector, and I'd have to figure out those angles based off of this one angle down here. It is easier to just decompose one vector. So I will tilt my axes as tradition dictates. This is how, as far as I know, people have been solving these force diagram problems for, I don't know what the history is, but for a while at least. So we're tilting our axes. That means that this vector mg needs to be decomposed into its vertical and horizontal components. And where would those point? This one I would point here, and this one I would point here. Now, from memory, we might say, okay, this one here is negative mg cosine theta. Or, I mean, do you need to say it's negative there? You just need to keep in mind that it's going to be negative when you plug it into formulas. So let me point something out there. Back here, for this example, I didn't say negative mg here. I just recalled that when I write my formula, it should be negative. So when I say negative mg, that's kind of unnecessary, to be honest. Maybe it's more necessary here because the vectors are all skewed, so it helps to remember that this is actually a negative vector by putting a negative there. But you don't really need it. It's just as long as when you set up your formulas, you remember that this is going to be subtracted. All right, and now from memory, we know that this one is mg sine theta. Okay. Oh, sorry, theta. Theta's 30 degrees. I could have, well, that's all right. That's like a generic setup. I should have put 30 degrees in there, but. And this is coming from that weird geometry, which was, can I redo it real quick? Sure. Let's see. Maybe, how about this separate piece of paper? Just decomposing that mg. So we have a 30-degree, oops. Okay, if this is 30 degrees, this is a right angle, and this is 60 degrees. What's happening? Where is mg? This side is mg. Okay. Now I'm making a new triangle, kind of back here, that is parallel, so this side of the triangle, so I'm taking like a new right triangle and writing it over here with this side being parallel to the slope, parallel to this slope. That's this horizontal component of mg. It's just written down here, superimposed down here, or projected down here. And then I have this side being perpendicular to the slope. So remember, the slope keeps going. So I've got my horizontal side being parallel to the slope, as a good x vector should be, parallel to the x-axis, and my vertical vector running along the y-axis, as a good vertical vector should do. And this is 90 degrees here. Now, since I know that overall, this here I've defined as being perpendicular to the slope, this red line is perpendicular to this green slope, then that means that this total angle is 90 degrees, meaning that this should be 30 degrees. So this angle in here is 30 degrees. Well, if that is 30 degrees, and since that directly matches with the slope of my ramp, this is the angle I'd like to use, not the one down here, but I'd like to get them to match. So when I do my trig here, here's my triangle. Let me pull this triangle out and put it over here. My angle is now up here, and this side is mg. And this is the right angle. So this is this red and green triangle, just going right there. Now, this side then, how do I say? This is y, this is x. So x is going, well, let's see. Cosine of, goodness, there we go. Cosine of 30 degrees is equal to the side adjacent to the angle over the hypotenuse, y mg. That gives me that y, the y component, is equal to mg cosine of 30 degrees. So we see there, that's the reason why we expect y to be associated with the sine, not cosine. But that's just because in trig class you always learn about the angle down here. But what if it's the angle up here? Well, then everything flips. So by a similar fashion, x will equal mg mg sine of 30 degrees. So there's the geometry. Okay. Now I'm ready. Excuse me. Now I'm ready to start talking about the some of the forces in x and y directions. Now, I should also note that the object is at rest. Okay, that's good. That means it's not moving in any direction. So the sum of my forces in the x direction is equal to 0. It's not moving. It's not accelerating. Let's see. It's really more appropriate to say it's not accelerating. That's why the force is 0. But obviously, if it's not moving, definitely not accelerating. All right, so some of the forces in the x direction, looking at my picture, this is the x direction. So I've got my mg sine, well, which direction is positive? I'm going to say to the right, right? So mg sine theta minus that friction force is equal to 0. Moreover, I know, well, what can I do here? I can go ahead and just set these equal to each other, right? But moreover, I know that my friction force is dependent on normal force. It's dependent on how hard the surface is pushing up on the object. So that means, what am I saying there? Well, my friction force is equal to this coefficient of static friction times my normal force. Okay, and I think that's about as far as I can get there. Probably need to go find my normal force by going over here to the y direction, which I know is still the sum of the forces is 0. So I'm going to have my normal force minus that mg cosine theta, that's the stuff happening in the y direction, is equal to 0. Normal force then is equal to mg cosine theta. Now plug that in. Over here, I'm getting mg sine theta is equal to mu sub s, that coefficient, times mg cosine theta. Now, I may have gotten a little ahead of myself here because all I was asked to find is this. What was I asked to find? The static friction holding the object in place. So do I really need to tear everything apart like this? No. I could just go right from right here, right? Because all I'm asked for is, I was given all sorts of data. I said that I was given the angle, I was given, this is mg, the object's weight mg, I was given the angle, I was given coefficient of static friction. So really, all the way from back here I can solve the problem because my static friction force is equal to mg, which is 78.4, right, that's mg, times sine of 30 degrees. Whatever that is. Is sine of 30 1/2 or square root of 3 on 2? I forget. It is 1/2, so time, okay. 39.2. So, yeah, I'll be honest, I just kind of like forgot what the question was and just kept working the math here because I don't know, I just got ahead of myself. Didn't really need to go that far. But if we needed to, right, this would be really useful to look at. If, say for instance, we were asked to solve for that coefficient, what if we were given, yeah, actually that could have been a legit question to ask here, without even giving you any other kind of information, just the object's weight and the angle of elevation. I could ask you to find the coefficient of static friction that would hold this in place. So I actually just thought of a good question that could be asked about a situation like this. Say I didn't give the coefficient, no, what was I going to say? I did give the coefficient of kinetic, or rather static friction. What if I said, what angle, is this too tricky? This might be a bit tricky, but this would be like an intense problem maybe. What angle is the coefficient static friction strong enough to withstand? Withstand. In other words, like for a given coefficient of kinetic friction, 0.25, how strong of an angle can we generate before the object starts to slide? So like if I know that the coefficient of static friction is 0.25 for a quarter in this box, then, and I'm saying at 30 degrees it holds still, no problem, but how steep can I get the angle before it slides? That would be a good question. So how would you do that? Well, you would work from this relationship you got here, mg sine theta equals mu sub s times mg cosine theta. I would go ahead and say mg is going to cancel here. mg doesn't matter. Sine theta equals mu sub s cosine theta times cosine theta. And I'm given that coefficient of static friction is 0.25. I'm saying for that coefficient, what angle, how steep can the angle get before the object starts to slide? Well, what can I do here? Because I've got two trig functions, both with that angle built in, some angle that I'm looking for. Well, I'm definitely going to want to use inverse trig functions, but there's two separate ones. But what if I say, well, sine theta over cosine theta is equal to mu sub s, but that's just tangent theta. That means theta is going to be whatever tangent inverse of mu sub s is. In this case, 0.25. And what is that going to give me? In degrees. Let's see, I'm in degrees. I hope it doesn't give me a weird answer. Okay, so I calculated it. It does give me a weird answer, but I think I know what's going on. So theta is roughly 14 degrees, say approximately. So what does that mean? Because obviously the angle I gave was bigger. What that probably means is I should not have picked such a big object's weight. The weight was pretty large, 78.4 newtons. That's how many kilograms is that? That's 8 kilograms, and that's a pretty low coefficient of static friction. Like, recall that on aluminum on steel, which is pretty slick, that was like 0.6 for static friction, 0.61 for static friction. So this is like super slippery. I didn't really think about that. That's a pretty steep angle for a pretty heavy thing at a really slick coefficient of static friction. What this means is, in real life, this object would not stay still, but it doesn't change like how we solved it or anything. That's still okay. I just probably should have had some foresight and thought about that coefficient of static friction was a bit too small. This, though, what I wrote in blue, is pretty realistic. This could be a realistic problem that could be given based off of the without an angle, without a given angle. So based off of that, what I'm saying is that for a fairly heavy object, about 8 kilogram, 16 pounds or so, on a surface that's pretty slick, you could only tilt like 14 degrees before the object starts to slide. And that seems much more realistic there. Now, this was just an object at rest, right? So let's look at now an object, similar situation, on a slope, moving though, with constant velocity first. So of weight, 117.6 newtons is being pushed up a 25-degree slope at a constant velocity. So I don't think we've looked at one of these before where the object is being pushed up the hill, but we'll look at it at a constant velocity. Okay. How strong must the applied force be? So the applied force is the force that's being pushed up the ramp, like a person pushing an object up a ramp. How strong must their applied force be to maintain that constant velocity? Okay, what else do I need to say? Coefficient of kinetic friction. I need to write that down. Assume a coefficient of kinetic friction of 0.7. All right. Without even worrying about how I'm going to solve it yet, I'm just going to go ahead and draw a picture. Here's my 25-degree angle. All right, here's my object. I know my normal force perpendicular to the slope. I know that my gravity points straight down perpendicular to the surface, the actual surface of the ground there, so that's mg. That's mg there. I know that there is an applied force pushing up the hill. I also know that there is friction pointing down the hill now. Why is friction pointing down the hill? Oh, wait a second. Okay, I had to pause and think about that, so let me explain why I just got confused. I was thinking, wait, friction is also opposing gravity, right? So like if the object was sliding down the hill, then friction would be opposing gravity trying to push back up the hill. But in this case, overall, the object is moving up. So since the object overall is moving up, being pushed up the slope, then that means that friction is indeed pushing down against that motion. And that's kinetic friction, because the object is moving. Even if the object's moving at a constant velocity, so that should immediately, you're thinking zero acceleration, and that's good, but it is still kinetic friction. Friction being kinetic doesn't depend on if the object's accelerating or not. It depends on if the object is moving or not. So that means we are dealing with kinetic friction here. I also need to go ahead and decompose my gravity vectors, which are going to be, just from memory, I'm going to say mg cosine theta, and I'll just remember that that should be negative when I plug it in to my formulas. And mg, I've run out of room. Too many forces. Let's try to draw it down here. Mg sine theta, pushing that way. All right, some of the forces in the y direction first, why not, are going to be 0 because the object's not accelerating up or down. Only, how many forces? Most of my forces are in the x direction. I think I've only got normal force and mg cosine theta in the y direction. So normal force minus mg cosine theta is, see there I'm remembering that it's negative. So I didn't write the negative there this time. I feel like it's understood, it's pointing down, so it's negative. And that's telling me that Fn, or my normal force, is equal to mg cosine theta. I'm sure that will come into play later. Some of the forces in the x direction is also equal to 0 because the object is moving up with a constant velocity. So 0 acceleration overall in the x direction. However, there is a lot going on. Now I need to be careful about what's positive and negative here. I have my friction, which is positive, because that direction is positive. I have my, wait, did we define that direction? Yes, okay. I wanted to make sure that's what we did last time too. Mg sine theta, if pointing to the right is positive, so mg sine theta is positive. And then minus that applied force, which is negative because it's pointing. So here you may be thinking, but down is positive and up is negative. No, it's not that. It's that right is positive and left is negative. That's what's going on here. That's why these two are both positive and this one is negative. And together, all together, is that it? Yes, 1, 2, 3, yep, summing to 0. All right, let's go ahead and use what I know about my friction force, that it should be mu sub k times the normal force, and then plus mg sine theta minus fa equals 0. And then I'll say that Fn, which is over here, so mu sub k times Fn, which is mg cosine theta, plus mg sine theta minus fa is equal to 0. Finally, my applied force should be equal to this, right? Just adding applied force over, flipping the equation over. Mu sub k mg cosine theta plus mg sine theta. So F sub A is equal to 0.7. mg is the weight, so 117.6. That was the weight. There, I'll wrap these in parentheses. So that's mu sub k times the weight times cosine of 25 degrees. Running out of room here. Plus the second term, which is mg sine theta. So mg, remember, is the weight. I was given the weight. I was not given just kilograms, not just mass, right? I was straight up given newtons, so a weight. And then times sine of 25 degrees. So I got 120, what was it? 124.31 newtons for my applied force needed to maintain an upward push at a constant velocity. So a fairly strong force, but that kind of makes sense because the object's weight is pretty, does it make sense? The object's weight is pretty heavy. The angle's fairly low, but the coefficient of kinetic friction was fairly high, 0.7. So pushing this object up the hill does sound like it would be pretty difficult. So needing a fairly high force there to do that. Alright, so how about... Alright, I had to scrub that previous example, so here we go, starting with an object, redoing this, so here we go. Alright. Now for an object sliding down a ramp or a hill, whatever, a slope, with acceleration. An object slides down a 45-degree ramp with constant acceleration. Assume the coefficient of kinetic friction is 0.5. Find the acceleration. Alright, first thing we want to do is draw a picture of this. So 45-degree angle right there. Overall, this thing does have acceleration down the hill. We're going to want to remember that for sure. Was not given the weight or the mass of the object, but I do know I should have a normal force. I should have a normal force perpendicular to the surface. I should have gravity perpendicular to the actual surface of the Earth. Normal force perpendicular to the slope. Gravity perpendicular to the ground. And then I have friction. So this thing is overall has acceleration, positive x acceleration down the hill. So friction is opposing that motion. Friction is pointing up the hill, and it is kinetic friction. Gravity, of course, must be decomposed into mg cosine theta, which will be a negative, right? It's going down down the y-axis. And then positive mg sine theta going to the right. So mg sine theta is the only thing pushing this thing down the hill, or down the ramp. Alright, so let's look at y direction first. Sum of the forces in the y direction is 0, because it's not accelerating in the y direction. My forces in the y direction are a positive normal force minus a mg cosine theta. See, only stuff happening in the y direction. And of course I end up with this nice relationship right there. Normal force is equal to mg cosine theta. That will of course come into play whoops, sum of the forces in the x direction is not 0. There is an overall acceleration, so there's an overall force, ma, here, where the acceleration is what we're looking for. My forces in the x direction are a positive mg sine theta minus a friction force, and that's equal to my overall force. By definition, my friction force is equal to mu sub k times the normal force. My normal force, by this relationship, I have that, so I have mg sine theta minus mu sub k times mg cosine theta, and that's equal to ma. Now notice I wasn't given the mass, but the mass doesn't matter here. The mass is just going to divide out. All of these terms have mass, so as long as mass is not 0, I can divide all of them by mass and it goes away. And mass is not 0, we have to assume that, of course. So all of these terms, mass just drops right off, disappears. Nice. And now I'm ready to find acceleration. I'll flip it over. Let me just write the a on this side. G is 9.8, then sine of 45 degrees minus mu sub k, which is that 0.5 coefficient of kinetic friction, then times 9.8, and then cosine, 45 degrees, there we go. Went ahead and calculated this, and I got a is equal to 3.46 meters per second, excuse me, squared. 3.46 meters per second squared. So that's pretty quick. But it's a pretty steep hill. 45 degrees is fairly steep. And that's a kind of a low coefficient of kinetic friction. So it makes sense that this thing would be kind of speeding up quite a bit. Okay, so now let's look at some tension force problems where we have to decompose tension vectors. Let's see, an object of weight 525 newtons is suspended by two ropes, as shown in the figure. So sometimes it's easier in the problem to literally just give a picture instead of trying to describe what the angle of the ropes are at and everything like that. So let's say we have some object and some rope. Let's see, attaching it like this to a ceiling over here maybe, and then another rope. Let's see, how complicated do I want to make this? Just do another like horizontal rope attached to a wall here. Okay. And let's say that the angle right there is definitely past 90, let's say 125 degrees. Oh yeah, what's the question? Find the tension in the ropes. It's like the cat burglar question. That problem too, but slightly different. Because I gave the angle in a different spot and different weight and everything. Okay. Okay, so drawing my forces on this, I have my mg, that's the weight, which I was actually given as 525 newtons. I have a tension force pulling up at an angle like this of, let's see, I'll call this, let's see, T1, or I'll call it T2, and this one pulling this way, I'll call that one T1. Okay, so notice T2 is really doing most of the work to hold this thing up, because T1 does not have any vertical component, it's just horizontal. That means when I decompose T2 into a vertical and horizontal piece, the vertical piece of T2 is the only thing keeping this object from falling, really. So let's look at that. Oh, what do we need to look at? We need to look at decomposing T2. So, bit of geometry coming. We need to know this is T2. This angle is 125 degrees. I want to know the vertical component of T2 and the horizontal component of T2. Okay, nice, good, good, good. But what is this angle? This angle is 55 degrees. Right? Yes, 55 degrees. Okay. This is my X side, this is my Y side. So X is going to end up being, well, X is adjacent, so this one is going to be T2 cosine of theta, and Y is going to be T2 sine of theta. It just depends on where your angle is given. You know, sometimes you got to work the geometry, you know, to find out how these things are going to, how the components are going to be acting. All right, so there's T2 decomposed into its vertical component being T2 sine theta, and this horizontal component being T2 cosine theta. Okay, some of the forces in the y direction is 0. The object is at rest, it's suspended, it's at rest. So that means my positive T2 sine theta force minus that mg should be 0. And also the sum of my forces in the x direction are also 0 because the object is suspended. So that means that my positive T2 cosine theta minus T1 should be equal to 0. So those two forces, positive one and the negative one, should be 0. So you see we're getting a relationship over here of T2 sine theta equals mg, and T2 is equal to mg over sine theta. So we can go ahead and find that. T2 is equal to mg, which is 525 newtons, over sine of 55 degrees. So T2 equals is that right? Yeah, I guess so. 640.91 newtons. And then over here, T1 is equal to T2 cosine theta. So T1 is equal to 640.91 newtons. Oops, I didn't want to put the unit there. Just 640.91 times cosine of 55 degrees. Now really, I guess I should only be keeping like at most 3 significant figures because that's what I was given in the problem. So maybe I should say 641 newtons, and then right up here I'll say T1 is equal to 641 times cos, just because in the problem I was given 3 significant figures, and also in my angle 3 significant figures, so I should stick with that. So here, what is that going to be? What is cosine? Let's see, 55 cosine and times 641. Oh, come on. 367.6, so 368 newtons. There they are. There's T1 and T2. Okay, so let's look at a pulley problem now. How do I phrase this? Two masses hanging over a pulley. Two masses so they're being held at rest. One mass is 5 kilograms and the other is 8 kilograms. Find the tension in the rope and the acceleration once the objects are released. So there's no table, they're just two masses hanging over a pulley, and we want to see, they're held at rest. One is heavier than the other, so we expect it to pull the other one. And we want to know the tension and the acceleration once the objects are released, and it seems like, how could we ever know that? Doesn't seem like we have enough information. Well, let's start with drawing a picture. I'll draw the lighter one on the left, 5 kilogram mass hanging over some pulley, and then a 8 kilogram mass here. So they're being held at rest, and we expect when the person lets go, this one is going to pull down with some overall acceleration. This one is going to be pulled up with some overall acceleration. It is a vector. I didn't mean to do that. I mean, if I'm going to introduce vector notation again here, I'm going to have to go back and put vectors over every single thing except for mass and coefficients of kinetic friction, so I don't want to do that. Okay, free body diagrams. What's going on here? First of all, I have M1G. I'll call this M1 for mass 1. And M2G, whoops, forgot the arrow. M2G pulling down. M2G pulling down on this one. I have tension pulling up on both of these. Right? When this is released, this one is getting pulled up. The tension is pulling it up. And also, the tension is pulling up on this one because this mass over here is pulling on this mass. It's both of the tensions are pulling up. The rope is not pushing the thing down, right? All right, so and there's nothing happening in the x direction. Should I say that? Yeah. All right. Let me see. Okay. So the sum of the forces in the y direction for mass 1 are equal to 0. Right, I have T minus M1, no, it's not 0, sorry, I'm just out of it right now. It's not 0, it's M1A, because there is an overall acceleration up, M1A. So this is equal to M1A. Now for mass 2, the sum of the forces in the y direction are equal to M1 times negative A. It's the same acceleration, just pointing down on the other mass. So here I have that same tension force, it's the same tension, it's the same rope, same tension force, minus M2G is equal to M2 negative A. This is the second mass. Okay. So when the object is falling, the acceleration is negative. This object is being lifted, so its acceleration is positive, but they are equal in magnitude. And now notice that I have two equations with two unknown variables. I have unknown tension force and I have unknown acceleration. So I can make a system of equations, if that rings a bell, which we've done. I may not have called it that, but what we're going to do is say t, I'll solve for t here. T is equal to m1a plus m1g. And then I'm going to plug that in right there for that t. So m1a plus m1g minus m2g is equal to negative m2a. So just this equation, but plugging in this for t. And now I'm going to solve for a. Okay, so I'm going to, what's these? I'll add this term over and subtract these two. So I'll have, in the end, m2a plus m1a equals m2g minus m1g. So scooting this across, so those change signs, and then scooting this across, so it changes positive, and this stayed put. And now I'll factor an a out. A little bit, maybe a little bit more intense of a problem, but still good to look at. And now solving for a, go ahead and divide that whole term over, that whole sum, m2 plus m1, and that will be what a is. So I've got a is equal to 8 times 9.8 minus 5 times 9.8 all over 8 plus 5. Those are the masses, 8 kilogram, 5 kilogram. And I'm getting 8 times 9.8 minus 5 times 9.8 divided by 13. Acceleration is equal to 2. Now, if I follow my significant figures rule, I've only got one. I'm getting 2.26 meters per second squared, but maybe if I follow the significant figure rule, I guess I should just say 2 meters per second squared. Seems like sometimes, though, the significant figure rule gets abandoned. So you just gotta, it just depends on, you know, what the question, hopefully a question on an exam or a quiz would specify what you should round to. Or it's a multiple choice, so it becomes obvious what you should pick. Yeah, so that is finding acceleration. So what are some of the big assumptions here are that acceleration is the same in both directions, just of opposite sign, and that also the tensions are the same. That's kind of necessary. Without that, you can't get very far in this problem, because all we were given is the masses of each thing. Okay. Okay, I think that is it for chapter 4. There's also the problems, which are endless, that could possibly involve kinematics as well, like problem 6. But those should tend to look, once you see anything that says like time is involved, or distance, or velocity, you should be thinking kinematics. So that problem 6 is a good example where they give you distance and time, which is enough to solve for acceleration instead of having to do all these crazy force diagrams to find acceleration. And then once you find acceleration, you're able to solve for whatever the rest of the problem is. So just keep in mind that you have kinematics as a tool, and it should be, I won't say obvious, but you should see some like key phrases that let you know to use kinematics, like if you're given time or distance or velocity. All right, that is chapter 4.